Hello, fifth period. So here are our notes for 4.2 factoring special case polynomials. So we're going to look at three different methods to factor polynomials. These polynomials will be different than our last section because our exponents will no longer be a 2 for a quadratic equation. We'll have exponents of higher powers such as 3, 4, 5, and 6. So the first method I'd like to talk about is using grouping. So whenever I have a 4-term polynomial, I'm going to think about using grouping to solve it. For example, this polynomial has 1, 2, 3, 4 terms. So factor by grouping would be a great method to try. So I'm going to group my first two and my last two terms together. And I'm going to look for a GCF out of the first two terms, and I see my x squared. And I get x plus 3 left over when I factor that out. And in my last two terms, if I hope to get an x plus 3 when I factor, I'll have to be factoring out a negative 4 so that I would get a positive x and a positive 3. I notice that I have the same binomial in both terms, so I'm going to pull that out, get x plus 3 times x squared minus 4. At this point, I could set my factors equal to 0 and solve and get the correct answer. However, I'm going to factor one more time to show you this polynomial in fully factored form. X squared minus 4 is really dots. It's the difference of two squares. So I need to factor it so that I can have my polynomial in my fully factored form. If you remember when I had the difference of two squares, it would factor into plus and minus the square root of my 4. So x plus 2, x minus 2. And if I FOILed this back, I would get x squared minus 4. So this is fully factored. And I'm going to set each of my factors equal to 0. X plus 3 equals 0. X plus 2 equals 0. X minus 2 equals 0. And I would get x equals negative 3, x equals negative 2, and x equals positive 2. This is 1, 2, 3 real roots. Those are my x-intercepts, those are my zeros. And notice that I have a third degree polynomial. So I should get 3 roots from my third degree polynomial. So let's take a look at this next one. There's also 1, 2, 3, 4 terms. But before I start factoring by grouping, I also notice that each term has a factor of 3 in common. So I'm going to go ahead and take out my GCF. My numbers become a little smaller and more manageable. So I have 3 times x cubed minus 2x squared plus 5x minus 10. And I begin my factor by grouping. I group the first two and the last two. And so once I do that, I'm going to use brackets because this will help me not get confused by all my parentheses. Just right there on the counter. So in the first two terms, I have an x squared in common. I have an x minus 2. The second two terms, I have a 5 in common. Again, I get an x minus 2 after I factor it out. And I notice then that I have an x minus 2 in common. So let's go ahead and factor that out of both terms. Then I would have an x squared left over and a plus 5 left over. This is fully factored because x squared plus 5 does not factor anymore. So I would set both of my factors equal to 0. I'm not going to set 3 equal to 0 because 3 equals 0 does not make any sense. So I have my x minus 2 equal to 0 and my x squared plus 5 equal to 0. When I solve this, I get x equal to 2. This is one real root. When I solve x squared plus 5 equal to 0, I'm going to solve by taking the square root of both sides. So I'm going to subtract 5 over. I get x squared equals negative 5. And now I'm going to take the square root of both sides. And I get x equals plus or minus. The square root of 5 does not simplify. However, the negative I can take out as I. The square root of negative 1 is I. So I'm going to get plus or minus I, square root of 5. And this is 2 non-real roots. So this would be my 1, 2, 3 roots for my third degree polynomial. So this is how I could handle a problem that has 4 terms. 4 terms. I might try factor by grouping. So what if my polynomial only has 3 terms? So we do something that we call quadratic style. I'm going to factor these using the diamond method that we did when we factored quadratics. But notice that my exponents, in this case a 4, in this case a 5, I don't have an x squared that I'm using. So that's why we call it quadratic style in quotes. It's similar, it's done the same way, but my exponents will no longer be a 2. So in this case, I notice I have an x to the 4th and an x squared. In order to do quadratic style, I need to have this set up. If you remember in the last unit, we'd have an x squared term, an x term, and a constant term in my trinomial. So now I have an x to the 4th term, an x squared term, and a constant term. So I could begin factoring by trying to figure out what multiplies to -5 while at the same time adding to -4. And I'm thinking about using 5 and 1, and if my 5 is negative, then they would multiply to -5 and then they would add to -4. So because my a is 1, I can simply put my side numbers into my parentheses. I don't have to take it into factor by grouping. However, unlike last unit when we'd write an x and an x inside our parentheses, now when I multiply my first term, I need to get an x to the 4th. So I'm actually going to write an x squared and an x squared. You'll notice that when I multiply x squared times x squared, I do get x to the 4th. If I insert my -5 and my +1 into my parentheses, and I continue my FOIL, I would get a -5x squared. I would get a plus x squared. That would give me my -4x squared in the middle, and then -5 times +1 would give me my -5 for my last term. So this is fully factored. I cannot reduce either one of these, so I'm going to set each of my factors equal to 0, x minus 5 equals 0, and x squared plus 1 equals to 0. And I'm going to solve by adding 5 over. Get x squared equals 5, and I'm going to take the square root of both sides so that I get x equals plus or minus the square root of 5. This is 2 real roots. I'm not sure what the square root of 5 is off the top of my head, but I believe it's around 2.2. So this is plus or minus 2.2 on my x-axis. Those are 2 real roots. Here I'm going to subtract 1 over, and I get x squared equals -1. And then I'm going to take the square root of both sides. So in this case, I get x equals plus or minus, and I know the square root of -1 is I. So I get plus or minus I. In this case, this would be my 2 non-real roots. And so I have 1, 2, 3, 4 roots from my 4th degree polynomial. So as I get ready to do example 6, I realize that I have an x to the 5th. I should get 5 roots when I do this problem. So I notice that it only has 3 terms. So this may be quadratic style as well. I'm going to first factor out a GCF though, because I notice I have an x to the 5th, an x cubed, and an x term. This does not fit my quadratic style setup of my x to the 4th, x squared, and my constant term. So looking carefully, I notice that these have a 3x in common. So I'm going to take 3x out of each term, my GCF. And I get 2x to the 4th minus 17x squared minus 9. And now I look to see that I do have an x to the 4th term, an x squared term, and a constant term. So I can try my quadratic style graphing, or my quadratic style factoring. So at the top I have -18, and at the bottom I have -17. I want it to multiply to -18 by adding to -17. That would be -18 and 1. So since my a is 2, I can't just put those 2 numbers into my parentheses. I've got a little bit of work to do. So I'm going to bring them back over and put it into factor by grouping. I keep my 2x to the 4th. I bring over my -18, but it's not -18x. It's -18x squared. So then I bring over my 1 as plus 1x squared, and then bring down my -9. So I've rewritten my negative 17x squared as negative 18x squared plus 1x squared. I'm going to group my first two and group my second two. So I get 3x equals, and then inside here, or I'm sorry, 0 equals 3x times inside here, this has a 2x squared in common. I would get x squared minus 9 left over. This has an x squared minus 9 already, so I'm only going to factor out a 1 so that I keep my x squared minus 9. And now I notice that both terms have an x squared minus 9 in common, so I'm going to factor that out. And I get 0 equals 3x times x squared minus 9 times 2x squared plus 1. If I set each of my terms equal to 0, I would be getting the correct answers at this point. However, it isn't fully factored. X squared minus 9 does continue to factor. I'm going to factor for one more step. This is my dots, my difference of two squares. So I'm going to factor it into x minus 3, x plus 3, times my 2x squared plus 1. Now this is fully factored. This would be completely factored form of my original 6x to the 5th polynomial. So I'm going to set each of my terms equal to 0. 3x equals 0, x minus 3 equals 0, x plus 3 equals 0, and finally 2x squared plus 1 equals 0. When I solve these, I would get x equals 0, x equals 3, x equals negative 3, and finally here 2x squared equals negative 1, x squared equals negative 1/2. When I take the square root of both sides, I'm going to go ahead and pull out the square root of negative 1. I would get plus or minus I square root of 1/2. This then would be my two non-real roots. This would be my 3 real roots over here. 1, 2, 3 real roots, 1, 2 non-real roots, and it's 5 total roots for my 5th degree polynomial. One last type of factoring that comes up when we factor higher order polynomials is the sum and difference of two cubes. So the sum and difference of two cubes was a formula. It was a pattern. So first of all, I recognize that I have two perfect cubes here. X cubed is x being cubed, and 8 is 2 being cubed. So my cubed roots would be x and 2. So if you remember, this factors into a binomial times a trinomial. So I write what I see, I write what I have. I have a plus sign in my binomial, so I have a plus sign in my binomial, and my two cubed roots are x and 2. And then in my trinomial, I have one minus sign in my formula, and since it's not in my binomial, it will be in my trinomial. And then I square, multiply, square. So in this case, I would get x squared times 2 times x is 2x, and then 2 squared is 4. So this is my difference of my sum of two squares, factored. So let's set that equal to 0 to solve it. So in this case, this does not factor, this trinomial. There's nothing that multiplies by 4 to 4 when it adds to negative 2. So when I set my x plus 2 equal to 0, I can get my x equals negative 2. This is one real root. However, when I set my x squared minus 2x plus 4 equal to 0, since I cannot factor it, I'm left with either doing quadratic style or doing, quadratic formula, or completing the square. Personally, when the a value is 1 and when the b value is even, I generally complete the square. If you wanted to take 1, negative 2, and 4 and put it into the quadratic formula, you will end up with the same answer that I'm going to get. So I'm going to complete the square by moving the 4 to the other side. And then I take my b, divide by 2 and square it. Negative 1 squared is 1, and I add 1 to this left side. I'm going to add 1 to the right side. And then I get on the left side x minus 1 squared equals negative 3. This is where I'm going to take the square root of both sides. I'm going to get x minus 1 equals, the square root of -3 would have me bring out an I, so I get plus or minus I rad 3. To finish this off, I'm just going to move my 1 over. I get x equals 1 plus or minus I rad 3. And this is my two non-real roots, roots. And so here I have my 1, 2, 3 roots from my third degree polynomial. Before I leave you, I want to show you the common mistake that's made with the sum and difference of two cubes. So some students see x cubed plus 8 equals 0, and they choose to solve by taking cubed roots, which actually isn't a method to use here. Let me show you what happens. If I subtract the 8 over, I get 3x cubed equals -8. And if I take the cubed root of both sides, if you remember back to Unit 2, I can actually take the cubed root of -8. There's no I in it, it's just -2. If you think about the math, -2 times -2 would give you 4, times another -2 would give you -8. The problem is this is just one real root. I've just lost my other two non-real roots by doing this. So this is not a method in which you can solve x cubed plus 8 for its roots. I have to use the sum of two cubes. So we'll continue this in class on when I see you, and we'll continue working in 4.2. Thank you very much.